Okay, in this video, I'd like to do number 1 and 2 on your homework with you to go over a couple other minor details. All right, on number 1, it says calculate the magnitude and direction of the electric force that acts between a positive 15 microcoulomb charge and a positive 3 millicoulomb charge that are 40 centimeters away or apart from each other. All right, so I blew this up over here so I could write a little bit bigger. And I made a mistake, so I fixed it here. I want to talk about the units of the charge. So I already told you that a coulomb is a really, really big value. So it's not common to have charges that have a magnitude like 3 coulombs. Instead, microcoulomb is very common, and micro is the metric prefix 10 to the negative 6. So I'm going to draw this out. So positive 15 microcoulomb. So I'm going to circle it. And then I now have a plus 3. This is millicoulomb, like millimeter, milliliter, millicoulomb charge. And if I could mentally turn each of the charges into a dot, and I connected their dots, they would be 40 centimeters apart. But I have to measure my distance in meters, so I'm going to write down 0.4. All right, so my equation, Coulomb's law, is going to give me the magnitude, and that's going to be KQQ over D squared. It's okay, since these are small charges, if you want to use lowercase q. I don't know, I'm not very consistent about that. All right, so the K is always going to be the constant, Coulomb's law constant, 9 times 10 to the 9. That's an easy one to remember. All right, the value of the first charge is 15 microcoulombs. What I put in here has to be in coulombs. So 15 in a micro means times 10 to the negative 6. That's what micro means. And then I have 3 millicoulombs. 3 milli is 10 to the negative 3. And I just was lucky that these were both positive, so it didn't confuse me. But even if they were negative, I do not put the negatives in. And then the distance apart, and then I square them. I hope when we multiply this together, we get this number here. I'll be honest, I did not verify that. And so that's the magnitude of the charge. But now I have to do the direction. And the direction is when you start to think about, are they attracted to each other or do they repel? I have a positive and a positive. That tells me that they want to repel each other. So then I have to add the direction away. So the direction for forces used to be like north, south, east, west, up, down, left, right. Now it's toward or away. All right, let's look at number 2 then. Number 2. Number 2 says, for comparison, let's compare the gravitational force of attraction and the electric force of attraction or repulsion between 2 protons in the nucleus of an atom. 2 protons in the nucleus of an atom. All right, so inside the nucleus, they're pretty close together. So it says calculate the electric force that exists between 2 protons that are 5 times 10 to the negative 15 meters apart. So I'm going to start by drawing a picture of my Q. I need to know what the charge is for a proton. So maybe you already forgot that, but let me see if I can dig it out real quick. I need to know the charge of a proton. Right here. The charge of a proton, 1.6 times 10 to the negative 19. So a proton would be a positive 1.6 times 10 to the negative 19 coulombs. Then I have to circle it. And then I have another one of those, 1.6 times 10 to the negative 19 coulombs, and I got to circle it. Doesn't all fit in there. All right, so the force, electric force, is going to be KQQ over d squared. So that's 9 times 10 to the 9th. Both of those q's have the same value. So I could go QQ, or I could just do like q squared. 1.6 times 10 to the negative 19 squared over, I'll just do this, over, they are 5 times 10 to the negative 15 meters apart, but I got to square that value. Again, I did not number crunch this, so I hope I did my math right the first time, but I got an answer of 2.9 or 9.216 newtons. And because positive, positive, they are repelling each other. That's why I included the word away. All right, so now let's do the gravitational force of attraction. So not only are protons charged particles, protons are also masses. So now I'm going to draw a picture of the mass of a proton. So here's the mass of a proton. And I now have to write in the mass of a proton. I looked that up on the internet. 1.67 times 10 to the minus 27. All right, so I'm going to have another proton because I'm sure there's another proton very nearby. Times 10 to the negative 27. And they are the same distance apart. But now I'm calculating the gravitational force of attraction, which is this equation. M over d squared. And this is going to be 6.67 times 10 to the minus 11. And my mass, 1.67 times 10 to the negative 27. I could repeat that, or I could just put the squared. And again, they are very close together. And when I number crunch, I get that answer. That's way smaller than that. And we didn't do this back in the day, but now I'm going to add it on. What's the direction? Well, they are attracted to each other, like they're attracted to each other. So I would have to add on toward. Every time I do gravitational force, it's toward. They're always attracted to each other. All right, the main point that I wanted to show here is that we're using very small numbers for the Q's, and I was using very small numbers for the masses. But I get very different answers. The electric force compared to the gravitational force. The electric force is way, way, way bigger than the gravitational force. Always. I mean, look at that. 9 newtons, something to the negative 36 newtons. And the reason for that is the constant. Look at the fudge factors. Newton came up with his fudge factor, his constant of the negative 11th power. And Coulomb's law constant is to the 9th power. And because of these values, those constants, the electric force answer should always be way, way, way bigger than the gravitational force. So much so that when we're talking about things inside the nucleus of an atom, we talk about the charges. We don't even mention their masses. Their masses are there, but they're so insignificant that their charge supersedes that. So in this whole unit of electricity and magnetism, we are going to be talking about the electric force, and we're going to be almost ignoring the mass of the particles because the mass is so insignificant compared to the topics in this particular unit. Okay, I hope this is enough to get you going. And as always, post your answers and solutions on the discussion board and be helpful to others. Okay.